Hello again. It's time to start talking about molecular geometry. This might be a little bit tough. You have to memorize a lot of things. You have to be able to draw, even just only a little bit, but still, a little bit's more than nothing. And it helps to be able to think about things in 3 dimensions. So this can be kind of annoying. But being able to think about molecular geometry is very useful for understanding molecular behaviors. So we're going to have to just dive right in. Now, the first thing we're talking about is VSEPR. VSEPR. Okay. That is Valence-Shell Electron-Pair, that is a terrible A, pair repulsion. Okay. And this is a model to explain the molecular geometries that we're seeing. Okay. So we're talking about pairs of electrons in the valence shell of the atom, and they repel one another. Okay. So you just look at the central atom, and you look at all the things bonded to it, and you know they want to get as far apart from one another as possible. So because, like charges repel. So Valence-Shell Electron-Pair Repulsion. It doesn't sound quite as cool as laser, but what are you going to do? All right. So you have to consider different things when looking at Valence-Shell Electron-Pair Repulsion theory. Okay. First off is electron domains, which is looking at not exactly electron pairs. It's looking at the places where electrons reside around the central atom. Once you've counted those up, it's just a matter of counting, you can get the electron domain geometry. That is to say, what shape is formed by the electron domains when they spread out in space around the central atom. Then you look at molecular geometry. Okay? Non-bonding pairs are invisible. All we can see are atoms. So what shape is left over when you remove the non-bonding pair from what we can see? So, an electron domain is a region in space where electrons live. Okay? And an electron domain is a bond or a non-bonding pair. Okay? Now, bond does not mean that a single bond is 1, double bond is 2, triple bond is 3. No. When we're talking about electron domains, a single bond is 1 domain. A double bond, 1 domain. Triple bond, 1 domain. Okay. So, when you look at ammonia, ammonia has 1, 2, 3, 4 domains. When you look at carbon dioxide, carbon has 1, 2 domains. Okay. So a single bond, double bond, triple bond, doesn't matter. Any kind of bond is a single electron domain. That is important to remember. So it's not pairs of electrons, it's just regions of space where electrons live. So once you've counted your electron domains, you know the electron domain geometry. It's just these, technically 6 kinds of electron domains, but only 5 shapes. Okay. So 1 electron domain means you've just got one thing bound to one other thing. Okay. It's a diatomic molecule of some kind. Could be one of the diatomic elements, Brinkelhoff, or it could be hydrogen chloride. But anything like that is going to have just 1 electron domain, and the shape is going to be linear. And one thing bound to another thing, 2 points, to define a line, and therefore it's just a straight line. That's the only shape it could ever possibly take. And it's not perfectly correct to talk about angles when you only have one thing bound to one other thing, because to make an angle you need 3 things, A, B, C. But we only have 2 things, so if you want to be technical about it, you want to be kind of a mathematician, kind of a wang, then, this isn't really right. But it's a straight line. Straight line means 180 degrees. So 2 things means it's linear, okay? Over here on the right, we have carbon bound to 2 oxygen atoms. Those oxygen atoms want to get as far apart from each other as possible, so they're on opposite sides from the carbon atom, which means they just make a straight line, and it is a linear molecule, because going from oxygen to oxygen, 180 degrees. These angles are important. They help us to understand the ways molecules interact and the way they fit together when we start talking about solids and liquids. All right. Next up, we have trigonal planar. Okay, that just means it's forming a flat triangle. Okay, might be kind of hard to see. Here in the middle, this green dot surrounded by 3 yellow dots is a trigonal planar molecule. Okay, it's just a flat triangle. That's as far apart as anything can get when you have 3 things. Okay. So over here, that's boron trifluoride. The fluorine-boron-fluorine angle, 120 degrees. So that is what you see here inside the boron trifluoride molecule, inside any trigonal planar molecule. Now, when you have 4 electron domains, they want to get as far apart as possible. They do not form a square. Instead, they make a tetrahedron. Remember, we have 3 dimensions available to us. We're not limited to a flat molecule. So they form a tetrahedron. A tetrahedron is one of the Platonic solids. One way of looking at it is like this. It is a pyramid with a triangular base. Okay, one of the Egyptian pyramids would have a square base, right? So this is not a tetrahedron. This is our tetrahedron. Now, another way is you say, okay, here is our central atom. Put this guy up here, this guy off to the left. It's also in the plane of the, pretend this is a blackboard. And then you have these 2 coming down. This is coming out of the board towards you. This dashed line back here, sometimes it's drawn more like that, is going back behind. Okay, so that's one of the ways we use to draw 3-dimensional molecules, is using a triangle to come out and a dashed line to go back behind. You will be seeing that more moving forward, so unfortunately you will have to get used to it. But any just straight line is in the plane. These 2 over here, okay, so in the plane, whereas these 2 over here are coming in and out of the board. Perhaps this might help you. Another way to visualize a tetrahedron. It's not perfect, but it might help, so I'll go ahead and throw it out there. Is you have a cube. If you have your central atom in the middle of the cube, then the 4 bonds, let's see, I'll use a different color for those. Your 4 bonds are going to different corners of the atom. Like I said, that's not perfect. It doesn't actually match the angles inside of a tetrahedral molecule. But it can help in some way to visualize the shape of a tetrahedron. Okay, and so the angles inside of a tetrahedron are 109.5 degrees. Okay. So when we're talking about the angles, we're talking about, let's go ahead and draw this guy again. Okay, let's draw a fresh tetrahedron so we can talk about the bond angles. Okay. So when we're talking about the bond angles, we're talking about this bond angle right here, or this one here, or this one here, or this one here, and so on. Okay, and those bond angles are 109.5 degrees. And it's not exactly 109.5, but it's close enough for government work. Okay. So So after our tetrahedron, we come up with one that might be a little easier to visualize. It is a trigonal bipyramid, or a shape that is trigonal bipyramidal. It's the difference between adjective and noun. So a straight line is linear. A flat triangle is trigonal planar. Okay? Trigonal means triangular, planar means flat. Tetrahedral is the shape of a tetrahedron. Okay? And trigonal bipyramidal is the adjective for describing a triangular double pyramid. Okay? So if you have a flat triangle, then you have a straight line going in and out of the middle of it. That'll tell you where the top and bottom of the shape is going to be. So you look at it edge on, you have a triangle going up, a pyramid going up, a pyramid going down. Okay, so this is the top view, and this is the side view of our trigonal bipyramid. So now I'll go ahead and try to draw it in all of its three-dimensional glory. Okay. All right, so we have a bond going down, a bond going up, a bond going to the right, and two bonds going to the left, one coming out at us, one going back away from us. Okay, so if this is this guy, okay, then this is the bond going right, this is the bond going to the back, and this is the bond coming out toward us. And when you draw that as an actual structure, you get something like this. This always defeats my drawing skills. Okay. But you have a triangle sitting on top, a pyramid sitting on top of another pyramid, this sort of butt to butt. And again, these are not your square-bottomed Egyptian pyramids. These have a triangular base. So that is the trigonal bipyramid, or a trigonal bipyramidal molecule. And you can see a better drawing of one right here, the orange guy connected to 5 green guys. This is the only one of our shapes where the interior angles are going to change. Okay. So for the other 4, the one that we've already covered so far, all of the interior angles are the same. Not so for this guy. For the trigonal bipyramid, you have 2 kinds of angles. Okay. The first is going from what we call the axial to the equatorial. Let me get a little bit more room. Equatorial. Because the way we've arranged it, we have a top and a bottom, then we have the 3 going around the middle. Okay, so that's sort of like the axis of the Earth versus the equator of the Earth. That's why we call these guys are axial and these guys are equatorial. So the bond angles, okay, so let's go ahead and label this guy in the middle as our central. Okay, so our axial to equatorial bond angle is 90 degrees. Okay, it's just a nice right angle there. And that's the same for all 3 of those bond angles. Okay. But when you're going from equatorial atom to equatorial atom, our bond angles are 120 degrees. So you can sort of think of the trigonal bipyramidal as taking a trigonal planar one and stabbing it right through the middle with a linear molecule. And so it's sort of combining the 2 in one. And that is the best you can get from 5 atoms arranged around a central atom in space. Okay. So that is the one that's going to give us some of the most trouble when we move forward to molecular geometries, because it's weird. And you're just going to have to remember 90 degrees and 120 degrees. And finally, our last shape is this guy over here on the right. If any of you is a giant nerd like me, you might recognize this as an octahedron or an 8-sided die. Octahedral is the adjective form of the shape. And that's what you get when you put 6 atoms around a central atom. They all get as far apart from one another as possible, and they make this nice square-based pyramid. And so you got two Egyptian pyramids butt to butt. Okay. And once again, it's nice and regular. Doesn't matter really where you look. The interior bond angles are always 90 degrees. So 2 to center to 3 is 90, 3 to center to 1, 90 degrees. All very, very regular. Okay. So those are the 6 shapes of the electron domain geometry. Let me go ahead and see if we can't draw those out relatively quickly. So you have linear, still linear. Then we have trig planar. Then we have tetrahedral. Then we have Trigonal Bipyramidal, or trig bipy. And then finally, we have Octahedron. All right, those are the 6, technically really just 5 shapes that you're going to have to remember anything about. You also need the bond angles, 180, 180, 120, 109.5, 90, and 120, and finally just 90 degrees. Moving forward, we're going to look at the molecular geometries. But that will have to wait for our following lecture. We will be ending lecture 12 here.